In this problem, we're going to look at the equation of motion for a physical pendulum that is motorized using Lagrange's method and Newton's method. So first, we'll look at Lagrange's. So we need to do L equals KE minus PE, which equals 1/2 I theta dot squared minus mgh. So we'll have L equals 1/2. Then I, for a physical pendulum, is 1/3 m L squared, theta dot squared, minus this mg, and this time the L distance, the center of gravity is halfway along the rod. So this distance is actually L over 2, distance to center of gravity. So we'll have mg L over 2 cos theta. And then we need to take derivatives. So del L del theta dot, we look at only the part with theta dot in it. So derivative of that is just dependent on the kinetic energy. So that will have 1/3 m L squared theta dot. And then del L del theta equals negative mg L over 2 sine theta. So then for the velocity derivative, we have to take the time derivative. So we'll go d dt of this equals the double dot. And then finally, we just put it into the equation. d dt del L del theta dot minus del L del theta equals external torque, which is given in the problem. So that equals 1/3 m L squared theta double dot plus m g L over 2 sine theta. So this is the equation of motion relating the external torque to the position and its derivatives. And we could also work this using Newton's method. So we'll look at that and show that we get the same answer. So looking here at the free body diagram, we've got this external torque, we've got the mass times gravity pulling down, and we know that since it's angular motion, then we need to write sum of the torques equals I alpha. So I, which is 1/3 m L squared times alpha, which is theta double dot, equals the torques. So we'll have this external torque here. It's trying to make it go counterclockwise, and then we'll have the weight trying to pull it clockwise, so that's mg, and its distance is L over 2 sine theta, because the distance there is this part. So this is L over 2 sine theta, force and perpendicular distance from the axis. So then if we rearrange this, then we have 1/3 m L squared theta double dot plus m g L over 2 sine theta equals torque. So this is the exact same equation as we got using Lagrange's method. So you could use either method to get the equation of motion for this problem. It doesn't really matter. the Lagrange method is good for very complicated systems, and Newton's method is good for systems that are less complicated or when acceleration comes out to be 0.